Okay, welcome everyone to the webinar on OpenMP. So this is the second webinar on OpenMP, and today we will have an introduction on OpenMP. So this is the second part. We have the first one last month, and the talk will be given by Christian Terboven from RWTH Aachen University and Michael Klemm from OpenMP. Thank you.
Hello, everybody. Good morning. So welcome to the second webinar on OpenMP with a focus on GPU programming with OpenMP. But before we go into the details of the GPU programming with OpenMP, first we have to learn about tasking. And I hope that by the end of today's webinar or the recording, you will understand that almost everything in OpenMP is a task. So I'm trying to say that with a smiley face here. In webinar number one, we learned about an OpenMP as a programming model itself. So we titled that the introduction. So right now we assume that you have a working knowledge of a parallel region, the work sharing constructs, data scoping, and the data environment. And Michael already gave you a brief introduction into OpenMP, something like a teaser for today's webinar. Today we will start with a review of webinar one. So if you have questions, please feel free to ask them. And we can summarize the solutions of we call them the homework assignments. So that means the exercises to get your hands used to OpenMP. And then I will start again with a motivation into tasking, however, with a slightly more complicated problem, and then explain the task model in OpenMP. Then Michael will take over and talk about task loops and task dependencies as kind of advanced features in tasking in OpenMP. And then I will finish the technical part with a discussion of so-called cutoff strategies, which are performance tunables or performance tuning approaches for task parallel programs. And then finally, we have some homework assignments again. The next three webinars, I can also add the one-sentence summary. So first, we will talk about non-uniform memory architectures and SIMD, meaning vectorization, which will bring us closer towards GPU and accelerator programming. And then in webinar 4, we will take a look into the introduction to offloading programming with OpenMP, obviously targeting GPUs. And then in webinar 5, we will cover advanced offloading topics. With that, I just have to change my slide deck here. And this is what I want to show. And I hand over to Michael.
Okay, so just a quick recap of the exercises that we did last time. But before we start that, are there any pressing questions that you guys want to ask real quick before we start with the real content of today's webinar?
Just a short question, maybe. Will this seminar also show combination with MPI for multi-node GPU or MP combination?
Probably yes. We thought about this, and we will likely add a couple of slides that explains the general interaction between OpenMP and MPI.
Thank you.
Yes, we can do that.
Okay, any other questions for the time being?
Well, if that's not the case, then let me quickly go through the exercises that we gave as a homework assignment. Next slide, please. So the first one is, a rather arbitrary example that doesn't really have a purpose except for burning a bunch of cycles on your CPU, so it computes sine and cosine of a bunch of numbers. And so one of the ways you can parallelize this is using the OpenMP work sharing. So there are two loops in this case where there is some computational meat in there. The first one is up and do some computation where we actually compute sine and cosine. So you could think about parallelizing that loop, or like Christian will show when he clicks once more, the second loop in the main function is actually the one that we decided to do. And since sine and cosine depend in their complexity and latency of calculation on the input values, we opted to use schedule dynamic so that there's some dynamic load balancing between the individual worker threads. And then since the code sums up the results that is coming back from the function call in a variable called result, you need to apply a reduction clause to sum up the individual local results of each of the threads and merge them or aggregate them into the global result of the computation. So that was hopefully an easy one to solve. As I said, not a real workload example. Next slide, please.
So why do you use schedule dynamic here, Mike?
Because sine and cosine can have different latency in computation, depending on which value you look at.
Yes, but so in this particular example, I just noticed that the outer loop iterates from 0 to dimension and calls the inner one with I, and the inner one iterates then from 0 to I times I. So that means the first iterations of index variable I are computationally rather cheap, because the inner loop goes from 0 to 1, 0 to 4, 0 to 9, and so forth. But the final ones go to 500 times 500, if I see that correctly. So that means the final ones are much more expensive. And if we would go by the default schedule, which is static, that I explained in the previous webinar, then we have a load imbalance here. And with schedule dynamic, we address it, in addition to what Michael just said.
All right, thank you.
Can I just a question, please?
Yes, please.
Actually, I was wondering, it is more efficient to use the reduction clauses or just to have an internal variable for each task and then reduce the variable? Like in this case, instead of doing reduction results, I can have like a local result for each private to each task where I perform the first reduction. And I can reduce these local results in the results variable. So which of the two ways would be the most performant one?
So, I mean, you can always roll your own reduction, right? So you could have, well, first of all, the code pattern will be way more complicated than what we're showing here, because now you would have to split the parallel region and the word sharing construct so that you can actually declare a thread local variable, right? It's always a bad idea to use an array where you use the index of the thread ID as an index into the array. So you shouldn't do that unless you introduce an additional stride so that each thread has its own local cache line to sum up its local result. So the code becomes way more complicated if you want to do all this. So you need like, let's roughly 5 to 10 lines more code rather than, reduction plus colon result. The other thing that you get from this is that at least a smart implementation will use like a tree shape reduction or piggyback the reduction on the final barrier of your parallel region, so that the reduction is in that form is actually potentially the most performant and most version than what you can do with your own reduction, because the implementation knows more about the machine, about the available instructions, and how to best execute that kind of operation. Right. Yes. So you can always, do that yourself, but usually we find that using the reduction variable is actually the most efficient version of the code.
Okay, yeah. Thanks.
And I agree with Michael, and I would like to generalize his statement. So if there's an abstraction for doing the low-level implementation, or as opposed to doing the low-level implementation of yourself, like what you sketched out versus using the reduction clause, I would always give the abstraction the first try, because then compiler and runtime can, to some extent or in parentheses, understand what you're trying to achieve here and try to come up with an optimal translation or execution scheme depending on your target architecture. For a certain architecture, sometimes you might be able to beat it, but not in general, because there's been a lot of effort invested into implementing just this line that you're seeing here. So it's several person years that have been invested into the compiler and the runtime, and it's really hard to beat that in general.
Okay, thanks.
Yes, and there were two questions that came in via the chat that are probably useful to answer as part of this general example. And we so the second one is it possible to use runtime schedule for this example? Yes, it is. Then you would get some additional flexibility by being able to control the used schedule, like dynamic, static, or guided from the command line. So either via using an environment variable or via the runtime API by calling omp set sket, so that you can, tell OpenMP which schedule to use. And the second question I would like to answer in the context of the matmul example. So if you go to the next one, that should actually be the matmul example. Yes. So let me first quickly give you the general idea here. So this is a very simplistic implementation of a matrix multiply. The usual disclaimer I make with these kind of examples is don't roll your own, use an existing DGEM implementation out of a BLAS library. But it's rather instructional to look at one of those examples, even though they don't give the best performance and are probably not comparable with the performance level of a CPU-tuned DGEM operation. So here, there's a bunch of functions, and obviously the one that you should have touched is the matmul_par one, which is short for parallel version. And so there are now 3 loops where you can add an OpenMP work sharing pragma to them, and we decided to put it on the outermost one. So Christian, please click.
Yes.
Yep. So we enumerate all the arrays, so A, B, C as shared from the webinar. You should know that we don't have to actually do this, but we consider it good style to actually do that. First, private for n, because that's not changing. And then we use schedule static here, because when you look at the loop, the load per loop iteration is at least close to be equal, so that you don't get any benefit from a dynamic schedule here. Then we have, there's a comment in there with a collapse 2. So you could play with that and basically merge the I and K loop into a IK product loop, so that you have more iterations that you can parallelize the loop with. All right, and now the question that came in, how could I have known beforehand if it's better to parallelize the inner or the outer loop? I tested and your solution was best. So first, thank you that we had the best solution. Is there a rule of thumb? And yes, there is. So usually one of the rule of thumbs is for parallelize the outer loop with threads and parallelize the inner loop with SIMD, which we will cover in the next webinar. All right, so that's a rough guideline on how to do this. The only exception to this rule is if your outer loop is like a timestamp loop that has to run sequential, then you opt to parallelize the second most outer loop instead. But generally, the rule of thumb always is multi-thread the outer loops, SIMDize the inner loops, and if you have MPI on top, you would then parallelize the outer loop with MPI across your MPI processes. Then one of the middle loops would then go to OpenMP, and then the innermost loops would be scheduled with SIMD instructions. And as an add-on on the previous question, what about opening the parallel region in the outer loop and using pragma-omp in the inner one? That is also a potential solution. But now so when you split that, you will have after each work sharing construct, and we'll come back to that later on when we talk about tasking. You would then have a barrier after each work sharing construct. So for each iteration of your outer loop, even if that one runs in parallel, you would get one barrier inside your parallel region for the work sharing construct, and that could actually add more overhead than in this simple example where we used the parallel 4 on the outer loop. All right, why don't you try collapse 3? That relates to the way how the loop is then laid out on the caches, and you take away from the compiler the opportunity to actually do SIMD. At least some compilers will not recognize that anymore. And then there's another question related to the example, IJK should not be private. They are in fact private. So the first rule is that if there's a work sharing construct, OpenMP automatically privatizes the loop counter of that associated loop. So in that case, even if I would have been declared outside, it would have been a private variable. And then K and J are declared as part of the for loop in the declaration part of that for loop. So K and J are automatically private by the scoping rules that Christian has laid out. Okay, and why is N declared first private instead of shared? Man, lots of questions. So this was a really good example. So by default, it would be shared, right? But then by the construction about how data is flowing in OpenMP, and this is now really about compiler internals, if you know that N is not going to be changed inside your parallel region, then you may want to declare it first private, because then you save the compiler from pointer accesses within the parallel region, and the compiler can then pretty much put N into a register because it's a private variable, and figure a couple of things out more easily. There are smart compilers who would be able to figure out that even though you declared it shared, it's actually a first private variable, but I wouldn't rely on that. So, you know, it's just a tiny performance optimization that you can make, and to also, you know, express to the programmer who probably reads your code in like 10 years that N is not supposed to change across the individual threads. It's just a matter of style and a tiny bit of performance. All right, I guess we have one more example slide.
Yes.
All right, now that one was a real complex example. I'm showing that this is a Cholesky factorization. That was already written in a way so that the matrix is blocked with block size TS. TS, I think, is short for tile size. And so there's a whole bunch of things in there, like a POTRF call to LAPAC, a symmetric rank update, dgems, and another rank update. So the question was, how could you parallelize that? And if you click once, then the first one is that you can parallelize over the I loop that pretty much feeds a number of blocks into the TRSM function of BLAS. And then the second loop, you can also parallelize where you process like, let me call it a quadratic number of blocks by calling dgem and the rank updates. And this naturally then assumes that the BLAS operations are single-threaded, so that they don't, in addition to the outer loop, launch additional threads. All right, there's actually another version of that, Cholesky opt, So if you wanna look at that, we parallelize slightly differently so that we get a little bit better performance behavior and model the data dependencies of the two nested loops in the second for the second parallel 4 slightly better. But today I will show you how you can do this with tasking in a more efficient and potentially also more readable way. All right, that's it.
Thank
Christian?
you for these excellent explanations, Michael, and thank you for monitoring the chat. So I trust that you will continue to take a look at the chat while I do the presenting, and later on we switch the roles, okay?
Yes, sir.
Good, so now I have to change again my screen setting here, and we continue. No, not with this one. Oh, come on, but with this one. And I have to share my screen. And then, sorry. Still not the right file. Now I clicked on the right file. So today's webinar is mainly about tasking in OpenMP. And I start with an introduction. So the first few slides are actually meant as a teaser. And then I'll take a closer look at the task model before Michael starts to cover more advanced topics. As I said, I want to motivate the use of tasks. So in the previous webinar, we learned about work sharing, which I believe I defined like something to distribute the work in the program, like for example, the loop iterations, onto a team of threads. Now, tasking is different. And this toy code, a Sudoku solver, might be a good motivation for why work sharing has certain limitations. So I assume you all know Sudoku, so we have to be careful according to the rules to find numbers that can be entered in either the rows or the columns. And this is a Sudoku board with a dimension 16 by 16. And we got this template. That means many fields are already been defined or set. And now we have to fill in the numbers into the empty fields. We can come up with a very simple algorithm. So the simplest algorithm to find all possible solutions is a brute force. And brute force means we try out all possible solutions. So first we start with an empty field. This is like we would start here in the top left corner, the field is empty. And then, being a brute force approach, we try out all the numbers, 1, 2, 3, 4, 5, and so forth. But for each number, we can verify or we can check if at this current position it is still a candidate, or if that number has already been used, for example, in the current row. And that's what I'm trying to indicate with a step 2a here. If the number is already been used, we can skip it. But if it's not being used at the current position, it could be or we could consider it the candidate and go to the next field. That would be this one here. And then continue with step 1. We have the empty field and then try out all the numbers. And sooner or later, we have tried out all possible solutions. How can we parallelize this with for work sharing, for example? Well, there's a for loop, or we could express it as a for loop. In each field, we have a loop of 1 to 16, if we have a 16 by 16 dimension Sudoku board. However, given the formulation of the algorithm, this is a recursive implementation. So that means if we would use, for example, parallel 4, the parallel region with a for work sharing construct in C and C++, at each field, we would create a new parallel region, meaning a new team of threads. And that means sooner or later, we would probably overload our system. Of course, we can implement thread management. So that means we limit the number of threads, we control that dynamically and so forth. But whatever you think of, it will not be really efficient, and it will be a lot of manual programming work. So what would be a better solution? The better solution for algorithms like this, so that means any recursive algorithm, but also any kind of irregular work, and we will cover that later on. These problems can be addressed with OpenMP tasking. So the main idea or the main difference is that we do not exactly describe how to, for example, distribute the loop iteration to a team of threads, but instead we express all the parallelism. That means we express all the independent units of works, which are the tasks. So we express all the independence within a given algorithm here. It looks very similar to what we already know. So we need a parallel, and with tasking, we always need a parallel region because we need a team of threads, at least in current OpenMP. But then I have this pragma OMP single here. Why is that? So think of the algorithm. We need only one stream of execution. That means we need something kind of serial or sequential to start with the first empty field and then examine all the numbers. However, we can go parallel as soon as we want to evaluate all the candidates for this field. So assume we have 8 candidates at this field. We can evaluate all those candidates in parallel. And then here again, we can evaluate all the candidates in parallel. Here again, we can evaluate all the candidates in parallel. So that means during the execution of the algorithm, that means in each recursive step, we can experience or exploit, I think that's a better word, more and more parallelism. We have to start sequentially. This is why we have a parallel. That means a team of thread and then a single. But then we can evaluate all the candidates in parallel. That means this is independent from all the others. If we create a copy of the Sudoku board, that's a technical detail. And all these independent evaluations are what we call or refer to as tasks. And at the very end, in order to, for example, print out the possible solutions and so forth, we need some kind of synchronization construct. I will explain in much more detail what pragma OMP task means and what pragma OMP taskwait means. For the time being, I just wanted to illustrate the OpenMP tasking construct, tasking concept. So that sounds simple. We just express a parallelism. However, this is the performance that we get from this simple code sketch. So what do we see here? This is the number of threads. And then the bluish boxes are the execution time shown here in seconds in runtime for this problem board that I've shown you. However, on a rather old system. And this grayish line shows the speed up. So what we can see here is that with 32 threads, and this machine uses hyperthreading. So let's say with 16 physical cores, we get a speed up of a little bit below 4. And that means this is certainly not impressive. So what I'm trying to say here is that by just expressing the parallelism and hoping that the runtime will take care of all the rest, some problems can profit from that. However, for some other problems, we have to have a better understanding and we have to invest more work. And this is why we are also covering I call it the tunables or the performance optimization strategies in the context of this webinar for OMP tasking. Now I have to switch again to a different slide deck. Okay, so let's dive right into tasking. And now I'm using the opportunity to discuss the details of the constructs that I just used to illustrate the concept. So what is a task? And I try to say it. A task is a work unit. That means some part of your code. And that implies that it consists of code to execute. And also some data, and in OpenMP that means there's a data environment, so that means references to shared variables or private variables and so forth. And the task is independent from all the other tasks, and that gives a runtime 2 choices. The task could be executed immediately, or it could be deferred. That means the runtime will execute the task at some point later. You can control what is the latest point in time at which a task may start, but you don't have immediate control or direct control if a task is executed right now or deferred to a little bit later. So what's the idea of this deferred task execution? If you remember back what I explained with the Sudoku board, we had the parallel single. So that means only one thread. Remember the single construct, one thread enters the body of the single, the others jump around and wait at the implied barrier. So we have only one thread that encountered this first empty field and then executed all the search for candidates and created for each candidate a task. So that means we have only one thread that is active and that this thread creates tasks. And deferred execution means it will create a task and put it onto a work queue and then continue right behind this task. It will encounter the next task construct. It will create the task, put it onto this work queue, and then again continue right behind this task. What do the other threads do? They jump around the single and wait at the implied barrier, or they wait at the end of the parallel region. And they can monitor the so-called work queue. So that means if the one thread that executed the body of the single construct is creating tasks and deferring its execution, the other threads could kick in, steal those tasks, without defining what stealing exactly means, but take these tasks and bring them to execution. So that's the general idea of how this program exploits parallelism. The runtime is responsible of mapping these tasks that are being created onto the team of threads that is available and running on multiple cores in our mental or in our execution model, so that we can actually get a speed up. Where do we get tasks from in OpenMP? And referring to this slide, I said everything in OpenMP is a task. So when we reach a parallel region, if you take a look at the OpenMP specification, it says that implicit tasks are being created, one per thread. So that means you already know to some extent tasks, although we talked about mapping iterations to threads. So it gets more interesting when we encounter a task construct. By then, an explicit task is being created. And this is what we're talking about in this webinar. Don't let yourself being confused by implicit task. It's just, I like to say it's just made it this way into the OpenMP spec to be compatible with everything, so that it fits together. So a task construct creates an explicit task, which is put into a work queue and can be executed by the creator thread or by the other threads available to the program. And I will add more details on that later on. There's also the task loop construct that creates tasks out of loop iterations in a loop. This is different from a work sharing construct, and Michael will add more details on that later on. And the task is being created when a target construct is encountered. And this is a fundamental construct to support offloading in OpenMP, which will be covered by us in much more detail when we talk about GPU programming in webinars number 4 and 5. But this is why we introduce tasking at this point in time, because the ideas here are fundamentally important to be able to program for GPUs. So let's take a closer look at the execution model with some example code, although I explained all the concepts already, at least this is what I believe. So I said tasks are useful for irregular or unstructured parallelism. Think of this while loop. As long as an expression is true, we have to do some work. We can't apply the for or the do work sharing constructs on such a code because we don't know the number of iterations. We don't know how much work is being created, so the runtime can't come up with a mapping of this work to the threads. And similarly, or what we have just seen in the Sudoku example, if we have a recursive algorithm, if we have a parallel region within each recursive call, we create more and more threads. This is in most cases not desirable because we would overload our system. And work sharing constructs cannot be nested. So that means we would need a new parallel at each recursion level. This is different from tasks. tasking because tasks can be nested. That means a task can create another task, which can create another task, and so forth. So how does it look like with tasking now in OpenMP? So it doesn't really matter if we say parallel single or parallel master, like in this example. So that means we have one thread that is executing the while loop here. And this thread is creating all the tasks. And the other threads within the parallel region are available to pick up these tasks and bring them to execution. But also the thread, the master thread or the initial thread here that's executing the while loop could also take up tasks and bring them to execution. And this is why the runtime has the freedom to decide if the task execution may be deferred or if a task may be executed immediately. How does it look like? So we have this parallel team of threads, the initial thread being marked with this darker black here and the others being in gray. And we have a task pool, and the runtime is responsible to map the task to the threads. That means, in my terms, to bring them to execution. And let me make that explicit here. We can have millions and millions of tasks being executed by 4 threads. Otherwise, our Sudoku example would not have been possible. Towards the end of this talk, we will take a look at the performance characteristics, and we will see that millions of tasks are being created. However, the runtime has a limited amount of memory that it may consume, and the buffers have a limited size, and this is why at some point, even in the execution of this while loop, the master thread might suspend the execution of the while loop, execute a task, and then resume the execution of the while loop later on, just to make sure that the memory management of the OpenMP runtime and so forth does not get out of control. I'm illustrating this, what I call the single creator scenario here, so that we have only one thread that is creating the tasks. But of course, it's also possible that multiple threads create tasks simultaneously. This is just an example here for while loops and for recursive algorithms. We have more examples later on. And as I said, that tasks can create other tasks, and also work chain constructs can create tasks and so forth. And I think I said it, all threads in the OpenMP team are candidates to execute tasks. And finally, this is the pragma OMP task construct. Again, the task consists of some code, which is defined here or denoted by the structure block. You know that from OpenMP already, and it's available in C, C++, and obviously also Fortran. And it takes a couple of clauses. And some of these clauses is what we will discuss in more detail later on. There are the clauses to define the data environment. You know that already. Private, first private, shared, there's default clause, and there's a special reduction or in reduction, this is how it's called, clause. We will discuss it with some examples in a few minutes. Allocate and detach are topics or clauses that we do not discuss in this webinar. So allocate deals with memory management if we want to allocate data for a task in a certain device or in a certain special kind of memory. And detach is something that we will cover in webinar number either 4 or 5, because it provides performance advantages or may provide performance advantages in particular with offloading. To support asynchronous function execution, for example. I will discuss if, mergeable, and final later on when talking about the cutoff strategies. So these are tunables to improve the performance. Michael will talk about task dependencies. And again, I will talk about tied and untied clauses, tasks in a minute or so. And then priority and affinity are also other performance tunables, and at least affinity will be covered in the next webinar. So quite a few clauses, but if you know the concept of, for example, first private, it will be the same in work sharing, parallel regions, tasking, SIMD, and also device programming or offloading. So once you have a grasp with a certain concept, you can apply it to all places in OpenMP. So I mentioned it, tasks can be tied or untied. What does that mean? So by default, a task is tied. And that means unless an untied clause, as shown here, has been specified. And that means if a task has been created, sooner or later it will be picked up by a certain thread. And that thread might be the thread that has created the task, but it might be a different one. And then the thread will be responsible to finish the task. That means to execute it until it has been ended. When does a task end? Well, at the end of the structured block. Why is this important? Well, a task might be suspended because of, for example, the taskyield directive that we will take a look at in a minute or so, or it might contain another task, a child task, a nested task, depending on what you might want to call it. And that means this outer task would be suspended, the inner task could be executed, or the inner task's execution could be deferred. As I said, it's up to the runtime. You give really a lot of freedom, but also responsibility of the scheduling to the runtime. But in many cases, believe me, it does a pretty good job. So if the outer task is being suspended, another thread might come and steal it and try to execute it. That means at the end of the inner task. However, by default, this is not allowed. And this is not allowed because tasks are being tied. That means as soon as a thread with a certain ID has picked up a task for execution, it is responsible to finish it, as I said before. That means if it suspends the execution of a task later on, that particular thread is responsible to resume the execution of a task. Tied tasks may cause a performance or scalability limitation. In particular, in examples that we have seen so far, where there's only one thread responsible or being allowed to create all the tasks. If that one thread suspends a task execution, picks up another task from the task queue and bring it to execution. And if that other task might be a rather long-running task, for example, include I/O, then the task queue might run empty and no other thread would be allowed to resume the task creation. Because this implicit task of the while loop or the single or whatever is by default tied. If you want to enable the runtime to switch the threads that are responsible to execute a task, we can specify the task to be untied. Why is that not the default? Well, think of any function or any functionality that makes use of the thread ID, for example, synchronization constructs, thread private data, we discussed it in the previous webinar, but also some other functions in glibc that have been made thread safe by thread privatization or other techniques, or any third-party code from which you do not know if it's safe to switch the thread that executes this code in between or in between two function calls and so forth. All these use cases would cause issues if suddenly within a task, the thread ID might change. And it will change if the thread executes, changes that executes a task. And this is by default, this is why by default tasks are tied. So untied gives the runtime a little bit more flexibility, but it might induce correctness problems unless you exactly know what's going to happen within a task. Unluckily, most runtimes do not really honor or follow this untied clause. That means they do not make any performance, or they do not draw any performance advantage from you specifying this clause. However, this is about to change. So I've seen the first commercial implementations of OpenMP now making use of that clause. By default, tasks are untied. That means the same thread is responsible to finish the task. Tasks can be suspended and resumed. I explained that at certain so-called task scheduling points. That means, for example, the creation of inner tasks, but also when the task yield clause is being encountered. So what does it mean? So if we have a task here at the task yield, the task might be suspended. The thread executing the task could do something different and then come back and resume the task and execute bar. Again, this is a performance tunable if certain tasks are found to be too long, too computationally, too heavy. Taking too long. So in the default case of tied tasks, that means this thread is responsible to first execute foo and then bar, and it might suspend the execution in between, but it will be responsible to bring the execution to the end. If you specify here the untied clause, also this might happen. The one thread is executing foo, and the other thread is executing bar later on, because the task yield enabled the runtime to switch the thread that is responsible to execute the task. Now let me explain the taskwait directive. It's a synchronization construct, and it waits for all direct childs. This is important for all kinds of task parallel recursive algorithms. So here we have a parallel single, and you know that pattern already, and then we have a task that creates another task, that creates another task, and then there's a task wait at the end. So these two tasks are being created by this, let me call it the outer task. So it looks like this. This is task A, and then we have tasks B and C, which are being created by task A, and that means, if you remember what I explained a few minutes earlier, the execution of task A might be suspended in favor of the execution of task B, or task B might be executed by a different thread. Both is possible. And then we have encounter this task wait. Which kind of task does task wait for? It waits only for direct childs, not any further descendants. So it waits only for tasks B and C. And in order to illustrate that, now let's assume C creates further tasks C1 and C2. These are not being waited for, I hope this is correct English, by the task wait construct. So the task wait waits only for direct childs, or children, I think this is the correct plural form, sorry, not any other further descendants. Otherwise, in this recursive example from the Sudoku code, but also many other codes, we would run into a deadlock, because then the runtime would wait for too many tasks. If you want to wait for all the tasks to be completed, there's the barrier. You know the barrier from the threads. It can only be passed after all the threads have encountered the barrier. And now with the introduction of tasking, a barrier means it can only be passed if all the threads have reached the barrier and all previously generated tasks have been completed. That means at the end of an either explicit or implicit barrier, all tasks are guaranteed to be completed as soon as the first thread is allowed or actually leaves the barrier. So the barrier semantic has been extended to wait for all threads and all tasks. Now, the task wait has been part of OpenMP 3, the initial OpenMP version that included support for tasking. Many people said, what can I do if I want to wait not only for B and C, but also for C1 and C2? And this is why we have the task group construct. So it's a structure, it contains a structured block. And at the end of the task group construct, by default, there's a synchronization point that waits for B, C, C1, and C2. So it waits for all the tasks that are being created within the extent, the dynamic extent of the task group. So that means even if within the task group, a function foo is being called in a different compilation unit that creates more tasks, these tasks are also being waited for by the task group construct. And do not confuse yourself. This code is different from the previous code. There, A was a task. Now A is a task group construct. We need that not only for synchronization, to express synchronization. We also need that to support reductions. And I have more examples, I think, on the following slide. But if you think of reductions and tasks, if you think about it a little bit, you can see possible complications, because the tasks, which might be executed sooner or later by a different thread, need some address, meaning a location to which to perform the reduction. And this also has to be synchronized. And if you remember how I introduced the reduction, let me call it naive synchronization would not have resulted in a scalable program. So reduction or implementations of reduction can be a little bit tricky. And this is why reductions in tasks do need some special support, both in the programming model, but also you as a programmer, you have to apply these functionality to enable compiler and runtime to generate code to actually generate scalable and performant reductions. Before I talk about reductions, I want to illustrate implications on the data environment with tasking. So we learned that task constructs do accept the shared, private, and first private scoping rules or scopes as clauses. Yeah? So if we say shared A, the variable is shared, private B, the variable B is private within the task. Remember, private means a new uninitialized copy, and shared means a reference to the original variable. And C means we have a new copy, but it's not uninitialized. It is initialized with the value of this original variable C at the time the task is being created. Not at the time the task is being executed, but at the time the task is being created. And first private is important for tasks because it allows us to capture the data environment into the tasks so that it has all the data it needs at the later point in time when it's going to be executed. And we can add the default clause, and we added a few more details here because we didn't cover that in the previous webinar. So at each pragma-OP parallel construct, a work sharing construct, but also the task construct, you can say default either shared or default none. What does that mean? Default shared means all the variables referenced in this construct or in the extent of this construct are being shared unless specified otherwise. And default none means the compiler will generate an error for all variables that are being referenced and not being part of any other scoping clause at the corresponding construct. So this is actually a good programming style. However, I have to admit it's not part of our examples to make sure that there's an explicit scope given for all variables that appear within the extent of a construct. So now let's take a look at some more scoping rules with respect to tasking. And with taking a look at the time, I want to be a little bit briefer here, although it's a pretty packed slide. Why can I be brief? Because the rules, or many rules from parallel region and work sharing constructs do apply to tasking as well. So what about thread private variables? If a variable is thread private, that means there's one per thread within the OpenMP parallel region. The variable within the task remains thread private. Dynamic storage variables, that means variables declared before the extent of the task construct are located on the heap and so forth, are by default shared. Similarly to a parallel region, what has been declared before is shared. Static variables or static data members in general are shared by default. So static variables, this is example 4, and static members of constructs, functions, and so forth are shared by default. And then finally, everything within a task that is called automatic storage location, at least in C and C++ programs, are private variables. That means the declaration is encountered by the threads or by the task, and then the variable is being created on the individual threads stack. It's a private variable, uninitialized. The rules from loop iteration variables that apply to work sharing constructs do not apply to task or task loop constructs. Sorry, not to task constructs, because the task construct, because it's not a work sharing construct anymore. So if you parallelize a while loop with an integer variable in there or something like that, or a for loop, and you create tasks in each iteration, then these variables are not being made private by default as they were with the for or do work sharing constructs introduced in the previous webinar. And now, finally, I have an example that puts everything together. So let me say here, this is a very ugly code. It might be confusing, but it illustrates all the corner cases. It doesn't do anything that's really meaningful. So what is the scope of A being within a task that is encountered within a parallel region that makes variable B private? So A is being declared outside of the function, and then C, that means it's declared at file scope, and that implies it's a static variable. Static variables, as I illustrated on the previous slide or the slide before, are always shared. And because it's a shared variable, in there it has a value of 1. Now let's take a look at B and C. B and C are declared within the function, so these are not static variables. They are declared before the parallel region. That means they would be made shared within the parallel region. But B has been declared private, by the private clause here. This will make, now let yourself not be confused, B a first private variable, while C will remain a shared variable. Why is that? So C is shared within the parallel region, and any shared variable in the context of task will remain shared. However, B has been made private in the parallel region. And now the task construct makes or has this additional role as shown here on the slide, that private variables will be made first private for a task. And I think this is the only complication and difference to data scoping from what you know already from the previous webinar. However, scoping is sometimes confusing. So why are private variables made first private on the task? And I think I try to hint at that. The tasks have to capture their environment. So think of this task being put onto a task queue and later on picked up possibly by a different thread. A private variable could be gone because it might have been declared locally at the scope, like D, which is gone at the time the task is finally being executed. And first private makes sure that the variable is being copied into the task, and that means there's a new instance of the variable per task, and the value at the time of the encountering of the task construct is being copied into this new private instance. And this is why D is also a first private variable. So D has a well-defined value of 4 here. This means it's being copied, but B has been made private here at the parallel region, and that means it's undefined within the parallel region. And in consequence, although it has been made first private for the task, it's also undefined within the task. However, many implementations will initialize it to 0, but this is not mandated by the OpenMP standard. And finally, think of variable E. If you think about it, that might be simple. It's a private variable because it's declared within the task. Finally, let's, toward the end of the introduction to tasking here, let's take a look at task reductions. So I said task reduction are a little bit more complicated because we need some, I would call it a reference or an anchor to which the tasks actually can do the reduction. And we also need a well-defined point at which the reduction has been completed. If we would just put a reduction clause on a task, there would be no well-defined point at when the last contribution to a reduction has been made. And this is why in many codes you will see that the task group construct is being used to implement reductions over task, even though including the synchronization at the end of the task group construct. If you want to do that, we have to say task reduction. We have to add that as a clause to the task group construct. The rest is similar to what we described earlier. There's a reduction operator and the variable. And at the tasks itself, we have to say in reduction, and then it will apply to the outer task group construct and contribute the partial results to the reduction in here. So there are two things to do. We need the task group construct with the task reduction clause, and we have to add the in reduction clause to the tasks that should participate within this reduction. If you don't want to add the task group construct, we can also just do it at the level of the parallel region, but then we have to give a corresponding hint to the runtime or to the compiler and the runtime. So why is that? If we would, you can assume that this is in a simple example, the compiler couldn't figure it out, but sometimes the tasks are not visible at the time the code is being compiled. So that means we have to make the compiler and the runtime aware of that there will be tasks in the parallel region that expect to be part of a reduction. So this is why modifiers to be added. So here we have again the operator, the variable, and this shall be part of a task reduction. And then we don't need the task group construct, but again, at the task, we have to say that it takes part in the reduction via the in reduction clause. Independent of if you use it at the parallel region with a task modifier, or if you use it at the task group construct as shown on the previous slide, the mechanism is more or less the same. However, we use slightly different words than what I used on my previous slide. So a variable is registered to be part of a task reduction. Just with parallel regions and work sharing construct, I was able to say there's a private variable per thread. Now we have to make sure that there's a special memory within allocated and managed by the runtime to which to perform reductions. The tasks all introduce or add their partial results according to the reduction operation during the course of the computation. And that means there could be special memory as part of each thread participating in the parallel region. And then at the end, either of the task group construct in the case of the previous slide, or here at the end of the parallel construct, all the partial results are being formed or added together in this particular example. So obviously with a reduction operation is being used to finally compute the global result of the reduction. I think I have a very brief illustration here, but this is a Fibonacci code, and Michael showed it in the previous webinar already. So what is special here? Nothing to what I explained so far. We have a parallel single. We have to have two tasks for the computation of the Fibonacci for X and Y. We have to manage the data environment here, and we have to add a task wait because we have to wait for this task to finish and that task to finish before we can actually compute the sum of X and Y. And since this is a homework assignment, I will not go into further details at this point in time. If you're interested, the slides are in the slide deck. And at the beginning of the next webinar, I will add the details that are part of this slide. So I will just go briefly over it. And with that, hand over to Michael, unless there are any urgent questions at the moment.
All right, can you pass the beach ball to me?
I will make you the host. Go for it.
All right. So I'm going to talk about task loop and task dependencies. So Christian already talked to you quite a bit about how you can make unstructured parallelism, so recursion or traversals of unbounded loops, and how you can parallelize that using OpenMP task. Now the question is, what if I do have something regular like a loop? And if my PowerPoint wouldn't fail on me, now it works. That's where the task loop construct comes in handy. So let me just give you a brief use case of one of the BLAS operations. Again, don't try this in that form. It's just for illustration, right? So you get your simple loop. It's all nicely balanced. It is all very regular, and it contains your Saxby formula. Now, if you want to turn that into an OpenMP task version, what you would have to do is, to be honest with you, a little bit cumbersome. So first of all, you would have to split the for loop running from 0 to size into 2 loops. One pretty much like the ones that I was showing in the cholesky example earlier this morning. You would split it into a loop that iterates across your loop iteration space using some tile size that you have to decide. Then you would have to compute for each of the tile size what is the lower bound and the upper bound of that particular tile. And then inside that tile, you would have your original computation. And splitting that loop pretty much involves that you have to rename your loop indices and make sure that they are somehow still doing the right thing and that you have the right iteration space after that transformation. Now, once we did this tiling, we can now add the OpenMP tasking to it, as I'm showing on the lower part of the left screen here. So, you know, parallel single, that's what you would do, like Christian was explaining, to kick off computation. Then this primary thread or this thread will run across the outer loop, enumerating all the tiles that you defined, and then for each of the tiles, so for each loop down here, you would then create an OpenMP task with all the enumerated privates, first, private, and shareds that you need to make it work. Now, for this example, this is rather manageable, right? We basically added like 4 to 5 lines of code. And so, you know, this is rather easy. Now, in a realistic code where you may have hundreds or even thousands of lines in your loops, getting the indices straight and renamed in the proper fashion is a bit of code refactoring that is cumbersome and likely error prone. So the way we approach this with OpenMP is that we basically provide a statement, a directive in OpenMP that exactly does this kind of code transformation for you, and this is the task loop construct. So instead of doing this cumbersome code transformation, you can just you know, use the task loop construct to parallelize a loop, a for or do loop, if you're a Fortran programmer, and turn that into OpenMP tasks that have a certain granularity. Here I'm actually showing already the grain size clause where you can influence the size of the tasks that are created, and basically, you know, the transformation that is shown on the, and get to a similar transformation that I'm showing on the left side. Right. So this is the idea. There's a whole bunch of clauses. Pretty much everything that Christian has told you also applies here. So we have very similar data environment clauses. It also supports reductions and introductions. So you can, you know, have a task loop either contribute to an existing task reduction, or you can create a new task reduction that only applies to the task loop construct. The ones that are specific to this construct are grain size and num tasks. So OpenMP gives you an option to either tell OpenMP what should be the size of the tasks that are created as part of the loop parallelization, or you can ask OpenMP with the num task clause how many tasks you want to be generated for this particular loop, and then OpenMP does the math for you to compute what the size of those chunks should be in terms of loop iterations. And then there's a bunch of other things like collapse, which basically are coming in from the work sharing constructs, where you can collapse a loop nest. There's no group, which basically tells OpenMP to not have a synchronization at the end of the task loop construct. By default, there would be the task loop construct would behave like if it were enclosed in a task group, so that execution only continues when all loop tasks plus the descendant tasks, so child tasks, grandchildren, and so forth, have been completed. All right, now let me compare work sharing versus task loop construct. Both look very, very similar, but they have a fundamental difference, right? On the left-hand side, we see a work sharing construct like Christian was showing last webinar, where we parallelize a do loop running from 1 to n, and we pretty much we count, which is, it's a bad pattern, but you know, it's illustrative. We just count how many iterations have been executed. So if you think about it, you know, if n is 1024 and we have 16 threads, what we assume is that each of the 16 threads gets like 1/16 of the loop iteration space, runs that loop chunk, and so that counter should be 1024 in the end, right? Which is the case. In the task loop example, you may probably think that you should be getting the same, but you actually get 16,384. Right, and this is kind of the fundamental difference between work sharing and task loop, because on the right hand side with task loop, what happens is that 16 threads are started here. Each of those 16 threads encounter the task loop construct, and instead of dividing the 1024 iterations across those 16 threads, each of the 16 threads launches the task loop construct. Right, so it behaves like a task construct. So you get 16 concurrent loops which are cut up into chunks. Right? So here you get one loop divided across 16 threads, and here you get 16 threads executing a loop from 1 to n. And when you sum up 16 times 1024, you end up with 16,384. All right? If you want to get similar behavior, you need to apply the single pattern that Christian and I was showing a couple of times already. So here what happens now is we launch 16 threads, but only one thread, one arbitrary thread, encounters the task loop construct and then starts dividing the 1024 loop iterations across you know, a multitude of tasks, which are then executed by the remaining 15 threads. And once the first thread here is done with cutting up the loop, it will join in to execute so that you get the full 16 threads executing OpenMP tasks. All right, and if you do this, you get the expected result. So this is something where you absolutely have to watch out. Task loop is really more like a task construct. So as many times as you encounter it, that many times you get the loop being executed. So if you you know, if you want to have it like behave like a work sharing construct, you have to add the single construct in front of it. All right, then the difference between the grain size and the num tasks construct. So on the left, the programmer specifies the tile size or the grain size, so how many loop iterations an OpenMP task should be executing when it is created for a particular loop chunk. On the right hand side, the programmer decides to use num tasks, so instead of the size of the task, we specify how many of those tasks we want. Naturally, those tasks must have at least one iteration, and since I was the lead when this feature was designed in OpenMP, I have to admit that this is probably a compromise that I shouldn't have made. So if you specify the grain size, the grain size actually doesn't mean that you get exactly TS iterations per loop chunk, but you get something that has at least grain size or at maximum 2 times what you specify as the value of the class. So this is kind of a compromise that we had to make in OpenMP to make everyone happy. By the way, later OpenMP versions then have a way so you can say strict here to remove that kind of flexibility of the implementation. The other thing is this needs to be a truly parallel loop, right? So the order of creation of loop tasks is completely unspecified. So the OpenMP implementation can look at the loop and say, well, you know, I'm going to start from the 0th iteration and run upwards. It can start creating the loop chunks from the end of the loop iteration space or anything in between. And the other thing that is not specified is the exact mechanism in which those tasks are being created. So an implementation, a naive implementation, can just create those loop chunks sequentially, while a more sophisticated implementation could do binary iteration splitting. So in a first step, it would split the loop into first half and second half. Each of these halves become an OpenMP task, and then these halves are further split into halves until the grain size is reached, or until the number of tasks have been reached, and then it starts executing. Okay, I already talked about the implicit task group that is around this task loop construct. So, you know, there's at the end down here, there's an implicit synchronization point where the encountering thread will wait until the task loop and all of its created loop tasks have been completed. And if you don't want that, you can use the no group clause to remove that implicit synchronization point. All right. Iteration spaces, I already kind of alluded to that. We do support the collapse clause with task loops, so you can specify how many loops should be collapsed. So pretty much if you use collapse 2, you end up with an ij loop down here that runs from sx to times sy. So this is kind of the standard way work sharing does this as well. And this kind of gives you more, iterations that are then distributed across OpenMP tasks, so that you get a little more meat for the parallelization and more parallelism out of your loop. All right, and then task reductions. Christian already kind of explained it. So where work sharing had a reduction clause, task loop has that too. So you can either have reduction here to create a new OpenMP task reduction that is just for this task loop, right? And it would then, do the magic to sum up individual contributions by the individual tasks and form a global result. Or you can, if you already have a task group that has a task reduction clause, so you already opened the task reduction and you want that task loop to also contribute a partial result to that reduction, you can use the in-reduction clause to tell the OpenMP tasks that are created for this task loop to contribute their result to that reduction that has been opened as part of this outermost task group. All right, task loop SIMD. We didn't talk about single instruction, multiple data yet. This is kind of a forward-looking cliffhanger, if you will, to the next webinar. So you can also marry the task loop construct with a SIMD construct, which would then cut the loop iteration space of a for loop into loop chunks, and then each of the loop chunks is fed into the SIMD vectorization unit of the compiler to also vectorize the loop body. Right. Let me now talk about task dependencies. So far, Christian and I were showing that tasks are independent units of work. So you can execute them in any particular order. Then we introduced a bunch of synchronization mechanisms. So the taskwait construct, the task group construct, and also OpenMP barriers, at which point tasks have to complete so that the encountering thread or the encountering task would bypass the taskwait, the task group, or the barrier construct, right? But what if you want some more flexible mechanism about how to describe in which particular order the OpenMP tasks should be executed? And this is where task dependencies come in. Right? So these are a way to define task execution constraints. So you basically provide a harness to the OpenMP implementation that describes in which order a particular set of tasks have to be executed so that there are no race conditions and your code is still behaving correctly. Let me give you an example. So in OpenMP 3.1, so this is pretty much what Christian and I were talking about in terms of task synchronization so far. So what we want to do here is we want to have a task that prints X on the console and then have another task to increment X. Obviously now the order in which we execute those two tasks is important, because if we execute this task first, we will see a different value printed on the console, right? So probably what we want to do is we want to make sure that this task runs first before this task is scheduled for execution. And the way to do this is to introduce an OpenMP taskwait construct, which pretty much only lets the generating task, the parent task, proceed to create that task once that task has finished, right? In OpenMP 4, what you can say is, I have a dependency between those two tasks, right? So here's an execution constraint where we say, this task here has an independency. It is going to read X, right? Whereas this task is going to read X and it's going to modify X. And this gives us an execution constraint that pretty much lets OpenMP schedule that task first for execution, because that task is going to be working on data and potentially destroy the state of this task, so that they have to be executed first task and then second task and not vice versa. So if you want to compare this in terms of what happens in execution, you can view the left-hand side to be something like a task barrier, where the blue task and the red task are separated by this black line, whereas in OpenMP 4, you get a graph that indicates that blue has to execute before red. Okay? And here's now the, in terms of going deeper into execution, what happens here is, in the OpenMP 3.1 example, you first create the task and you have to execute it, because then there's a task barrier, and the second task can only be created if the first task has been created and executed, right? Whereas in the second lower example, we can create the blue task, we can create the red task, and then there's this execution constraint that only schedules the red task on some executor thread once the blue task has finished execution. So you get a slightly different behavior in terms of when the tasks are created, but you get the additional benefit of synchronizing the task execution so that the tasks are executing in the right order. All right. Okay, here's the cholesky factorization that we looked at before, right? If we take the blocked version that we used for the work sharing hands-on sessions and convert them into tasks, you would see that you have a task for this function call, you can have a task for dgem, and you can have a task for the rank update. So this is pretty much similar to what we were showing with the work sharing constructs just now with OpenMP tasks. But now the thing is, you have to make sure that the TRSRM on the blocks has been completed before you can do the update on the trailing matrix, right? So before you can call dgem and rank update, you need to make sure that all TRSRM plus invocation have been finished. So you have to introduce a bunch of taskwait constructs, which pretty much gives you this lockstep behavior between the individual phases of purple, blue, and red, purple, blue, and red, purple, blue, and red. On the right-hand side with OpenMP 4, what I did instead is I now have OpenMP tasks, and I'm now describing what data they are consuming and what data they are producing. So for instance, if I go to the TRSM task again, it reads the AKK block as an input, and it also reads AKI as an input, and it produces a new version of that block by calling TSRM. Down here, dgem consumes JI, produces JI, and to do so, it consumes KI and KJ, right? And with that description and the actual loop indices, the OpenMP implementation can infer if this dgem invocation is actually working on a block that is coming from that BLAS invocation. Okay, so I'm now modeling kind of the data flow in this whole algorithm, and I come up with a task dependency graph that describes how these tasks are correlated with each other and what data they are working on. As an additional benefit, in this example, I couldn't parallelize the pod_rf, but with task dependencies and the way I can model this, I can even convert the pod_rf into an OpenMP task and create a little more parallelism by having another dot or node in my task dependency graph. All right, that actually gives you a little bit more performance. So the red line is the OpenMP task version from the left-hand side, and the blue part is showing, like, let's say 10% or maybe 15% more performance because we have more parallelism that we can exploit, and we can pull in tasks that are that have been completed. We can pull their execution in to fill idle execution threads. All right, so what's in the spec? There's the depend clause to the task construct. In OpenMP 4.5, we also did the depend clause to the target construct. This is a forward-looking reference to the GPU part of this webinar series. And then in OpenMP 5, we did a bunch of additional modifications that are more technicalities, but we also provide a new mechanism so that you have additional ways to express the data dependencies and how the tasks should be constrained in their execution. All right, so what do we have? So we have this depend class that takes a depend modifier, a dependency type, and then a bunch of list items, so variables or array references. You can specify in, out, and in, out. So this is an input dependency which expresses that the task is working and reading that data. Out means that the task is producing that data, and in-out is kind of the combination of those two. And for the sake of simplicity, I will ignore mutex in-out set and depend object. We will probably come back later to that if there's a real desire. All right. Okay, now what the mechanics are: a task cannot be executed until all the predecessor tasks are completed. So that means, according to the depend clause and the specification there, we can now infer the right order of execution so that tasks that are producing data are completed in the execution before a task that consumes the data is being scheduled for execution. So this is just what I already explained in a bit more wordy fashion. So if I give you an example, so here, we have a variable x, t1 is reading and producing x, t2 and t3 are reading x, and then t4 is also reading and writing x. So we get this shape of a task graph where t2 and t3 can only run if t1 have been completed. Those two can run in any particular order, at least in theory. And then T4 can only run if T2 and T3 have both completed execution. All right. Let me skip that one in the interest of time. The task dependencies are defined across sibling tasks. So that means there are some constraints on what you can specify and when the task dependencies have an actual effect. So suppose you have T1 here, that is an outer task to T11. And if T2 has also a dependency, this depend clause and this depend clause do not connect to each other because that task and that task are not sibling tasks. So that means they don't have the same parent task, right? If you want that, you would have to restructure the code so this outer task is gone, and so that this task construct and this task construct are on the same level in terms of the task structure. Right? Okay. The other thing is, and this is especially relevant to arrays, so either you specify identical or disjoint storage in the dependency. So that means if you have an array section up here that describes that this dependency is valid for array elements 50 to 100, right, or 99 elements, then this is different from specifying A, right? So the whole array. So if you go back to the cholesky example, it's basically the starting address of the array block that is used for dependency matching. It's not the full block instead. All right. Okay, and then there's a way to specify dependencies if you have a dynamic number of those. So say you have a algorithm that processes list elements, and so you have then a task that should depend on all the previous list elements that have been computed. Right, and there's no real way to express this unless you use the iterator clause, where you can say, okay, in this dependency clause, J is going to iterate from 0 to n, similar semantics as in C, so excluding n, so from 0 to n minus 1. And then you can say this is a list item. List item J is an input dependency for this second task, and so this depend clause will now match all the list items with index I that are produced by the first producer task. All right, let me skip that. This is more like for you to read up more of the specific aspects of task dependencies. Let me close with a use case, and hopefully all of you are able to stay like 5 minutes more. So sorry for running over this. Let's parallelize a Gauss-Seidel iterations. Right? So the idea here is for a number of time steps, you iterate across a two-dimensional grid over J, I, and J, and we pretty much apply this 5-point stencil that pretty much takes the north, south, east and west neighbors and averages those to produce the cell in the middle of this stencil. Now, the data dependencies in that particular examples are, as I just described, so up and down and left and right. So to compute this cell, you need input from that cell, from that cell, from that cell, and that cell. So there's a data dependency that you cannot easily get rid of if you want to parallelize it. Right? The typical approach is that you can compute the upper left corner, and then in the next wave, you can compute that diagonal. So you can compute this element, and that element. And then the next step, you can do this. All right? So pretty much what you have to do is you have to move or skew your loop like by 45 degrees, so that you get a wavefront that basically implements that pattern, right? And then you can use a OpenMP work sharing construct to pretty much parallelize across those diagonals, right? So if we do this, this is the code to do this, right? And you don't have to fully go through it, just pause the video on YouTube and read through it. It's rather cumbersome to do this. There's a bit of work involved to basically make this 45-degree shift, and then you can launch a parallel region across your time steps, and then for each wave along a diagonal, you can launch an OpenMP4 statement or construct to parallelize that diagonal loop, right? Now, the downside of this is, first of all, in the upper corner and the lower corner, the degree of parallelism will be rather low, right? Because, you know, the wave is getting smaller and smaller until you start again, and then you have to ramp up the full wave, you parallelize across your grid, and then you have to ramp down the wave again to do the next time step. Plus, after each work sharing construct, as we already discussed at the beginning of the webinar, at the red dot here, there is going to be a full barrier that involves all your threads that participate in parallel execution. That adds additional overhead on top of your execution. Now let's do that slightly differently. If we look at the parallelization again, once we are here at this point, we have completed the first two waves, right? So we could actually start a second wave that involves this element because we already computed those darker green ones, and we can have the first wave compute on the first diagonal, and we could, in theory, launch another wave up here, right? So we could do this pattern and start overlapping time step Tn in green and Tn plus 1 in blue, right? Now, if we are far along with those two waves, we can actually start a third one. So we can now have the green wave, the blue one, and the red one active at the same time. And if the grid is large enough, we can start multiple of those concurrent waves according to the n plus third, n plus fourth time step and exploit more parallelism, right? And the way we can do this is similar idea as before with work sharing. We do some blocking. So TS is again a block size in our grid. And for each of the blocks, we now launch an OpenMP task. Again, parallel single is the same pattern that you saw a couple of times already. So this kicks off the computation. And then we create an OpenMP task to compute a tile of the Gauss-Seidel grid. And for each of the tasks, we record what are the data dependencies. So the current block is being read and being produced by reading these 4 blocks. And if you look at this, these are exactly, the first dependency is this green block, the middle one, and the second, the input dependencies are those 4 blocks up, down, left, and right. And with that, we get a dependency description of how the blocks correlate to each other and how they depend on each other. And then the OpenMP implementation can schedule them at the right time. So, when the wave is far along, it will automatically pull in an OpenMP task from a new wave if there's an idle thread. All right. Does that give you anything? Yes, it does. Again, the red line is the previous solution with OpenMP work sharing, and then the blue line is the one that uses OpenMP tasking. And so while the OpenMP work sharing construct is a little faster for small thread counts, you see at some point, like at 24 threads, the tasking version with dependencies will take over because the synchronization overhead and the limitations in terms of parallelism are more severe and are penalizing the work sharing constructs, and we get a straight line up for the task dependency version of that code. All right, and then real quick, what we did in OpenMP 5 is the taskwait construct now also has a depend clause. And so what that gives you is if you want to create really, really large dependency graphs, you can now use the taskwait construct to inject synchronization nodes into the task graph so that you don't actually have to wait down here, right? But rather just insert like a synchronization point in your task dependency graph and create many, many nodes in your task graph, put those synchronization nodes in there to really have, like a generator that creates a task graph and then have an execution phase where you just spend time executing that task graph. All right. With that, I'm done, and we can talk about questions and answers. Thank you.
Thank you, Mike. So on our agenda, there was a final discussion of put all this into play to improve the performance and scalability of the Sudoku code. but I would like to move that to the beginning of the next meeting as a kind of a summary. So please continue with the exercises.
All right. Okay. So we also prepared a bunch of exercises again that you can work on before the next webinar. And the next webinar then will start with a quick recap of those exercises. So again, git clone, the URL is up there. It's the same as last time. We created a new subfolder webinar 2. There's a bunch of example codes, including the matmul example from previously, the cholesky example, Fibonacci, the Sudoku solver. So you can look at all those codes for the time being. And then you can type make, and again we stripped out the OpenMP directives from the actual source code, and there's also a solution folder again that you can look at if you are unsure what to do, or if you want to double check if your solution is similar to what we did. All right, that's all I had to say.
Okay, thank you very much. So I think we are a bit late, so maybe we shall close the webinar. So as usual, guys, I will post the video online on YouTube, and you will receive an email with all the information. And just remind that the next webinar will be on Tuesday, 16 March, so in 1 month, at 9 AM, as usual, on this channel. So thank you very much, Christian and Michael, for the great webinar, and see you next month. Bye, everyone.
Thank you. Bye-bye.